my lecture, there are 2 lectures left. I will prove this LP theory. But before I do that, maybe let me try to kind of give you some, I think, elementary but important remarks of about what we did, and it's at least psychologically is important. So review on what we did, and it's in each of the problem. Actually, you have to do similar things, but you have to develop new mathematics. So the key thing actually I want to say actually is a dialect or dialects of regularity theory. So let me quickly review what we did. Is we more or less did this picture is more or less like 1 by 1, then plus the PDE, and the smallness is typical. Then the picture we localize, we get squeezed. Right. So that's big. I mean, this give you the regularity. Then you iterate that picture, you get what you want. And but the thing's really a lot. That's really what it is. But if you think about psychologically, it's a lot deeper than that. It's say the result. Let me do this C alpha theory first, because that's a lot easier to see. Say, suppose you want to prove the following: u of x, u minus that. This something like that, right? And suppose this is the goal. Then what's that picture tells you? This is like a C2 alpha picture. The whole picture is you don't have a main line. This main line is like a polynomial. But C alpha theory is the main line would be a constant. Then the picture you squeeze would be tiny little bit. That's the holder picture. Then the C1 alpha picture, you see a line is made out of the term. You see the error is much smaller than any line. That's C1 alpha theory. C2 alpha theory is you always say the error you got is much smaller than the made out of the term. Otherwise, you don't see the regularity. But nevertheless, this is the goal. Then this goal actually is you can draw a very nice picture of it. In this case, maybe something like that, and that is cleared. And the real difficulty is what is U0. The difficulty is that it is there, but you are not supposed to know. It's global information, and if you linear equation that's given by the Poisson integral. And for nonlinear equation, you don't even have a formula, right? So, and if you examine again, this is actually there's a continuum number of inequalities. What do I mean? Is that for each x, that has to be true, right? It's for each particular x. If I say that is true, doesn't mean anything. This inequality is some information in continual fashion, and if you want to do something like continuum fashion is basically beyond human power, right? How can you do something continuum? It's pretty deep. Is this? But so then what this picture really means that we change this continuum into discrete, then discrete into one. That's actually the essence what we did. Let me write it down. This is continuum. Then we try to do it discrete. Discrete is actually following. It's equivalent to this. Is u of x minus u of 0, L infinity. You see, this is for any x in ball 1, right? We really prove it, you know. Morally, we did this. So we do this, r0 to the k, less or equals to r0 to the k, r alpha. Then for k equals to say, well, a 0, 1, 2, da da da. So you see, you see a quantum leap is a from proving a continuum number of inequalities to a countable number of inequalities, right? And we did that also. We not only did that, we did something. We changed this into the correct dialect. You know, is even better. But let me just try to explain this. Then, how do we prove this countable many? Many inequalities, right? So human being even lazier than that. I mean, continue we cannot do it. Then we do the countable. Countable is still too hard, you know. I mean, how do you do infinitely many things? We can't. What we do, we only do one, then induction. But each picture repeats itself, so we don't do one step. Then that's really what we did. So continuum into discrete into one iteration. So if you can do it from ball 1 to ball R0, actually you are done. It's pretty powerful about this. So this all the regularity theory like this. I mean, even including what Hydrogen did about Navier-Stokes equation. Is you really do one step, and that one step is mathematics. All the iteration is kind of, you know, it's like a basic training. You have to learn this, but the mathematical part, the math part, is this single step, and this vertical line, this line. That's the art, you know. Which view you look at the PDE give you the squeezing, and that you have to say the correct dialect. Usually the correct dialect is you do it the easy one, you know, is you go to Korea, the easiest language you speak is Korean. You know, English maybe you can make it, but not the best. Certainly not Chinese. So let me give you some examples to see this, and then there's at the very end all the embedding theorems. There are many embedding theorems. And they all say that, at least for Schroeder theory, for the holder theory of C alpha, C1 alpha, C2 alpha, is the world is beautiful. Is that no matter what kind of dialect you speak, the maths they are the same. I mean, that's really the essence of what we did. So So for example, dialects, right? If you look at this equation, there are really two easy ones. One is Maxim principle, right? One is energy estimate. So you just using that to speak out the regularity. Then for heat equation would be, this is like the energy, or L infinity, or actually anything in between. Same thing like that. Then let's do nonlinear ones. This is the harmonic map. Is the easiest harmonic map is this system. This is a harmonic map, say from a domain to say to a ball. It's minimizing this energy, but you minimizing with the constraint u equals to 1. It's like this. So this actually is the multiplier of that constraint. I mean, any constraint problem, you have the multiplier. The derivative has to be perpendicular to the level set, and that's parallel to the level set. So this is your PDE. It's clear, like if you say energy, right? That's the language is really in front of you. So you want use, and that's basically the theory. You want use energy to speak out the regularity. That's exactly what Schoen-Wullenbeck did. So for harmonic map, the correct thing is that you say in terms of energy, U minus a constant. You want to improve the constant approximation, but that disappears. Then you have to do it so that it's very close in the Holder fashion. This measures how big U is in a scaling invariant way. Why is that? This is the U of R0x H1 0 norm. I mean, maybe this is let me remind you that H1 norm is greater than U squared plus U squared. But if you only take the homogeneous part, people usually write this way, and if you do something more analytical, what you do is taking average. That's fairer comparison. So this really which is exactly equals to this. Then the crucial regularity is to show this becomes smaller. So if you go back to what Schoen-Wullenbeck did, is that they proved this thing. It's this. I mean, you can do a kind of half. I mean, actually, if you really follow the steps, although they didn't claim it, the proof implies this thing. You do see the Holder regularity if U is a minimizer. It doesn't mean you can really see this easily, but at least you can see this is quite convincing The thing is the following, is provided some smallness. What is smallness? Of course, you assume that is small. Then it's really clearly true, right? It's like it's a this list equals 1 because that's norm equals 1. If that thing is small, use almost harmonic. Use almost harmonic, U would be almost like constant. Then you hit it. But however, you need an energy minimizer to hit the energy somehow. So to reach this step, sometimes it's harder. But the geometry of the regularity, exactly same picture. Okay, and another example. So let me give you all the examples. Say minimum surface. That is a surface that the mean curvature equals to 0, and then the first is the same thing as like locally minimize the area. Then what is the correct dialect? It's really in front of you because you talk about area, right? Then you use area. And say this is really the geologist did this. He said that if this S is very close to a plane in ball 1, and this closeness is crystal clear. Close you measured by area, right? Is it because that's more or less the only number you can use. Then the conclusion is that then also area minimizing. Then S is closer to another hyperplane in ball R. 0. And this closeness is again measured by area. Then how do you say it? Is the area of the surface intersect with the ball R 0, and close to a flat one, you measure the area of the in this way it's a hyper surface would be a TR. The flat n minus 1 dimensional disk. This thing decays. Is smaller, but the smaller is improved by the C1 alpha fashion. Is laser equals actually I can say half if I want R times area of S intersect with ball 1 minus area of T1. And he gave this a name that's called the axis. Axis. Okay. Then I won't do it. Hygiene did it yesterday. For Navier-Stokes equation, what do you do? Is use cube norm and the pressures 3/2 norm is very easy to get, and also iterates. then what you do is, under the smallness condition of that, those quantities improves. It's exactly like that. It's exactly this the C alpha theory using the local dialect of Navier-Stokes equation. So for any equation, what you do is the first fundamental step is actually as what we did is any estimate you have. I mean, it's like you need something. Without any estimate, you cannot say anything. You first, do you have anything? Then write that down. Then the second thing is that under smallness, if the smallness, that smallness says that term equals 0, the world is perfect. For example, in this case, if this equals 0, that has to be hyperplane. It's, like harmonic map. If this guy equals 0, this is harmonic. And everything can be said. It's like the limiting equation has a regularity. That's basically the really general view of the regularity. And then the foundation of all of this is what I said. Is that in any dialect, if you can show that, so this is basically says in any or almost any. In the norm you ever have seen, semi-norms, norms. There's nothing, there are no counter examples. I mean, you can make up counter example, all the useful norms. In any norm or semi-norm, if U is like U is like R to the alpha. U is like a, let me say, constant with error R to the R alpha for all points, and all points means x equals say ball 1, and all scales say R all this all equals bigger equals 1, then U is classically C alpha, and the same is true for C1 alpha, C2 alpha, and etc. Really, it's anything. Let me repeat what I did. So, say the classical picture is U of x minus U of y. This all equals. I mean, I always take equals 1. This holder continuous, right? For x, y, equals 1. This is a classical. Then dialect. You can say this in many ways. Let's say L2 is 1. So then you do it in most reasonable way. Is I say U of x minus I look at all points, say y in that scale R. Then there will be a constant. You don't have to even specify. This constant can be depends on R, can be depends on that. And this average, take square root. Then this behaves that way. Then you assume this soup for all R less than 1, bigger than 0, all Y is in ball 1, say. Actually, this you can even take inf if you want. Inf of the C in R1. It doesn't matter. But if I say this is 1, That exactly says that at each point, fixed point y, you can be approximated by some constant with error r to the alpha, right? In the L2 norm, right? R is a scale, y is the freedom. Now guess what? They are exactly. These two things, they are equivalent. The only thing is not so equivalent is because that this ball, if y like near the boundary, this might be go outside. But if you disregard that, this really literally means this. Maybe let me finish this line of thought. Then maybe I give you a proof of this fact. But that's the underlying thing, and there are lots of things implied by this. So let's look at H1 or H1 0. So I want to say U of x can be approximated by some constant. Then I take gradient. Then this is my error estimate in this scale. Then this is gradient of U of Rx squared for 1 square root. This if you dial it into unit ball, you get a fair comparison. And this of course you do it y, then if this decays, then you take soup. It can means for all r this, for all y in there. Guess what? This controls the use C alpha now. This is classical. And this is almost like identity. If you set it correct, it will be identity. But this you never can make this two identity. This is morally is that. But the only reason you don't have one identity is that not all the C alpha functions you can talk about the derivative. That's the only reason you don't have an identity. But these two, they're morally the same. They walk the same. They sleep the same. They eat the same. They're exactly the same. Okay, and you have unlimited ways to do it. And the 2 is not anything special. So you can change it to P. It's equally correct. You can take like second order derivative, any other derivative. So that would be it. So let me give you a quick proof. So all this, they are names. This called like maybe this called Mori embedding. This may be called the Capenato embedding. But this just very soothing. This is when that is true, everything is really, really nice. And the proof more or less the same. So let me try to give you a quick proof. I mean, I don't have tons of time to do this, but this say, for example, here. What we have proved so actually we proved like a discrete ones, right? The first you observe that this discrete and the continuum in this radius is they are equivalent. That's very easy to see, right? Because this implies this is maybe k. So if this is true, I say I first change the discrete to like a continuum in the radius. You do think this as the variable. Maybe not 1 anymore, it's like C bar. How do you prove that? These two are equivalent. So this clearly implies that up to a constant, right? So I only have to prove from here to here. Then that's actually rather easy. It's like for any r, this I claim this for any r plus that. So for any r is almost to r0 to the k. For some k, right? It's always you can always put this somewhere. So for example, then you just compute. I mean this u of r minus u. I do the bigger one. So if r is less or equals to r0 to the k, bigger or equals to r0 to the k plus 1, then I have this c k, let me do the ck squared. This clearly less or equals to the integral. It's trivial inequality. If this is true, because this is a subset of that. Right? Then what do? You say, then I do the average. Then this average right? But this is almost 1 through this inequality. It's almost 1, right? It's like the essence of this and the way you think is this line. Is r is almost that. Is proportional to upper bound by that, lower bound by multiple that. So these two are comparable. Means that's almost like compare with 1. So this less or equals to r0 to the k alpha. But this is almost r. They are comparable. Right? This is like maybe you have a constant. Maybe you have another constant r to the alpha. You switch those numbers for free. So continuum to discrete, they are the same. Then next, what you do is, since each scale u is approximated by some constant, and the convergence is this series, then these numbers, they have to behave really, really well. For example, let me draw a picture here. Say here's r over 2. So u in the whole here, u is almost like constant. The error is r to the alpha. Then here you approach by another constant there. The error is r over 2 to the alpha. But r over 2 to the alpha is almost r to the alpha, right? So I say a function in a bigger scale is almost 1 constant by r to the alpha. In half of the ball, close to another constant, the area is also r to the alpha. Then this two constant is distance is r to the alpha. There's no other way, right? You can write down a silly inequality to prove it, but intuitively there's nothing to prove, right? It's the proof exactly this. You just shrink the half ball, and not only that, this when there's true, you can actually switch the center. It doesn't matter. So the average here and average there, they all close. So this means that CR, if I indexing it, everything is really nice. CR of x minus CR of y less or equals to r to the alpha. It's like if you shake it, nothing changes. And not only that, it's like you can also do this for any s less or equals to r bigger equals to r over 2. I mean, you can draw a bigger ball. What's the difference? You already know this. Close to a constant. Then actually that's the proof. You see, CR to CR over 2 is first of all is r to the alpha. Then CR over 2 to CR over 4 is r to the 2. I mean, this is same constant here, alpha. Then you get CR to the 2 to the k minus CR to the 2 to the k plus 1 less or equals C. The same. You do it in all scales. Then this error, the adds. This is geometrical theories, right? This r to the alpha over 2. All those errors, they add together, is exactly something like that. The property of geometrical theories has a property that you adding all terms together is comparable with the leading term. Right? That's the property of geometrical theories. Then what does this tell you? This tells you that CR minus C infinity is less or equal to CR minus CR over 2 plus CR over 2 minus CR over 4 plus blah, blah, blah. But each of them is CR to the alpha plus C. I mean, this same constant, R over 2 to the alpha plus blah. But this is geometrical theories. This equals C1, say R to the alpha. That's why in mathematics, geometrical theory is so friendly. You can add. So, and this is the limit of this approximation lemma. But actually, those things are very close to the averages. So by Lebesgue differentiation theorem, those things has to be u of y for almost all y. Right? This Lebesgue differentiation theorem. This is since CR and the average of ball R. If you think about this also, R to the alpha, that has to be U guy, because U minus average. If U is close to a constant, then U's average also close to that constant. The average has nowhere to go. So you prove those things is convergent to his limit. So this is the average in R scale. This is the precise value of that function. Right? So what do you see it here? You look at X, look at Y. Right? So I knew if I draw a ball, say that ball R, then the value at the center, distance to the averages in this R scale, the area is R to the alpha. And also here, the U of Y with average here, the error is also r to the alpha. But this and that, they all close to, say, I draw another ball, say 3r or 2r. All the errors, all the average here and here. Look at this picture and the errors, the constant approximation here, the averages here and there. You swap them, the distance all r to the alpha. So what's that mean? Is a value from here to here, distance r to the r to the alpha. But what is r? R is anything. R in this picture, my r is just exactly x minus y. That's my r in that scale. You know, before the r can be anything, but this, when I look at this picture, I take r equals x minus 1. Then that's the end of the proof. It's really elementary. So the thing, this kind of things is like, the most important thing is that before you write down the proof, you almost say believe this should be true. And the really difficult part is the inductive step. It's number one step from ball 1 to ball r. You only think about that step. Anything after that, it's almost like a triviality. It's like homework for your students. But sometimes, like that's crucial step. Sometimes you spend years to think about it. And that's the thing. And of course, this picture, as I said, that is dialect free. Anything you can do this. Is it clear? You want me to write more lines? Okay, so now.
Why are you using the dialect?
Dialect is for each PDE, you have to say the local dialect. That's I choose the word. For Laplacian, you can say energy.
Scaling invariance?
No, it's the easiest available control of the solution. That's the dialect you have to speak. Say for biharmonic functions, you better use H2 norm. Right? It's that natural thing to do. Right? It's the easiest available norm so that the solution is under control in that thing. It don't have to be a norm. It can be a semi-norm. It can be anything, like IL3, IL4, anything.
I have one question. I mean, if you repeat this kind of process again and again,
yes,
to take kind of estimate, do you have to have a scaling invariance or?
No, it's this. That's actually a very important question. So you want to do this, and you need two things. You need either the equation of the scaling is invariant, or the equation improves.
You mean regularity?
No, the equation improves. The equation even closer than to the limiting equation than before. Because the main step, you need a smallness thing. And if you pull out the coordinate, you need another smallness thing. Now after you look at next step, the smallness thing improves, then that will be it. And they always have this kind of character. And actually, that's also connected to what is the crucial regularity. Say, for example, for minimum surface, it's kind of clear. Is you want to prove C1 because the tangent plane is really the crucial thing. If you want to prove C alpha theory of minimum surface, you'll go nowhere because the tangent plane will become wilder and wilder. You are going further and further away to the hyperplanes. So in order for the requirement, in order to really to answer your question, is exactly that important point. Is for minimum surface, you want to say the solution getting closer to a hyperplane, and that's boiled down to like the gradient is concentrated. When the gradient concentrated, the equation is closer to Laplacian. So you cannot prove Holder regularity for minimum surface as the first step. The first step may be ellipsis. Your scaling invariant estimate is ellipsis, but that's don't have any regularity yet. The first step regularity is C1 alpha. Only when you reach C1 alpha, the equation getting closer to Laplacian. For like a Schauder theory, is you can go all the way to C alpha estimate because it's closer to Laplacian, and the equation in divergent form. It depends on what kind of regularity you want to do. Say for Holder theory, you better assume AIG like a scaling invariant. That's exactly uniformly elliptic condition, and that's the groundbreaking regularity. You cannot go that. I mean, it's hard to imagine people to pull like a regularity less than that. Okay, so where was I? So it's pretty easy. Yeah, they have a so this is the C alpha theory or / Schauder theory, which covers like 90% of regularity theory, and the other things I want somehow, since I'm talking about here, let me do other connections with what I'm saying. For example, U is in W1P in ball 1. Then you want to say that how this norm, I mean, there's nothing to do with PDE, with this whole philosophy. So you want to say how U can approximate by a constant. It's actually is Poincare inequality. Is like this is true. And this that you can take a P, anything you want. Right? This is this scaling invariant Poincare inequality. Then you see, you just write it down. This average means 1 over R ball 1 and over P, 1 over P integral gradient U to the P ball R. And then this is finite, then this less or equals to C's gradient U's LP norm R to the 1 minus N over P. I mean, I absorb all the constant there. Then you see it's like W1P norm controls U's constant approximation by this exponent. If that exponent is positive, actually we just give a proof. U is that C alpha Holder continuous. We just proved it a moment ago. So this embedding theorem. And that exponent is actually not bad to think about. If this constant is negative, you think this kind of function or W1P function is C alpha for this alpha to be negative. It's actually a very good thing to think about it. And this thing really truly measures how smooth a W1P function is. And that's usually I call that's a smoothness index. So this means the the embedding theorem. So what we did is pretty strong. And this exponent should be called smoothness index. Then since I'm talking about that, let's compute this. Let me define W1P smoothness index is 1 minus Pn. Then take the liberty about the LP smoothness. Of course, I say 0 minus N over P. Right? I mean, you just threw one away. So, geometrically, if I give you a LP function, you see it's Holder continuous with negative exponent. And W1P function is that exponent. If that exponent is positive, you do see classical continuity. If that constant is negative, you see the quantum effect. And the punchline is next thing. And all the embedding theorem, leave the index, the smoothness index invariant. Let me explain that. So once you like this definition, how do you remember the index of solved embedding trace theorem? You don't have to remember them at all. So for example, W1P, people say it goes to W1Q, right? Let's do the silly computation. This is 1 over P over N, right? You agree, I did that computation. This has 0 minus Q over N, right? The smooth index. Let them equal. And then solved embedding actually says that if this identity is reasonable, then it's correct. If not reasonable, it's wrong. Reasonable means that if left-hand side is a positive number, you embed it to Holder continuous function. The quantum effect gets lost. It's classical. You don't hit the Q. But if left-hand side is negative number, the embedding is to some LQ, and the Q is computed this way. Nice, huh? Let's see H1 Rn plus. This has a trace on this Rn minus 1. Everybody knows this is H half. But how do you get half? It's actually because you do the restriction. Restriction never changes the smoothness, right? So this is 1 minus 2 over n. Then what's this guy's smoothness index? It's half minus this n minus 1 dimension. So it's n minus 1 over 2. And if they are equal, the world will be wonderful. And you check they are equal. Right? So in general, like W1P, you restrict to the function is WSP. But what is that S? Is 1 over Pn equals to S. The question mark is equals to Pn minus 1. Then this cancels. S equals 1 minus. Okay, so this covers the indices. Okay, so tomorrow I will talk about the LP theory, and I will give you preview. So Holder, you see U is getting approximate by constant. Then the LP, there is a deeper things of it which I will talk about tomorrow. The elementary thing is actually this. Say if I say a function, say this equals 1. Okay, suppose you want to prove something's LP norm equals 1. At least you want to prove something like that. then the easiest but very important thing is this bigger or equals to, say, this bigger equals, the set U is bigger or equals to T, right? Then when U bigger or equals to T, this bigger equals to T. And this implies that the measure of the set, this actually equals to this. The level set is less or equals to 1 over T to the P. So in essence, this is the Holder regularity of this function. I call this function rho of T at infinity. It's like this to a power, right? Of course, that's Holder regularity. And LP theory is what you want to do morally. This is a very rough estimate, but this is so close. It's like this inequality and this thing. If you think about it, it's very hard to tell the difference by naked eye, which I will really talk again. It's very difficult to tell the difference between this inequality and that inequality by naked eye. The meaning is from here to here, trivial, right? Then if I just add a little bit, this actually implies that, right? It's elementary. You can prove it. Who can tell if I say a function less or equal 1 over T to the 100 to 1 over T to the 100.00001? You can't. So the intuition about LP is actually the regularity of the distribution function at infinity. And what we proved, Holder theory, is the distribution at one point. The LP is kind of it's a value distribution nearby. At one point, you see the value concentrates, but the LP you see the distribution, like Holder regularity. So then Holder theory more or less says that if f behaves by a constant by certain power, then all the other second order derivatives decays exactly by that power. So LP theory, in some essence, is exactly that. If your distribution function f have some decays, you want to prove all the second order derivatives of U have the same kind of power. On the surface, it means that. But as a matter of fact, analytically, it's a lot deeper. So I will talk about that tomorrow.